The sport of basketball incorporates many principles of biomechanics. These principles are important both for performance and for injury concerns. We're going to focus on the performance side of things, specifically projectile motion, Magnus force, and ground reaction force. Watch the path of the basketball after the shooter releases it. It forms a parabolic arch that is typical of an object following projectile motion. Once the ball is released, the only force acting on it is gravity. Because gravity is the only force acting on the ball, we assume that acceleration is constant. With acceleration being constant, we can use these three formulas to find out different properties of the ball while it is in flight. Knowing the height of the shooter, the height of the basket, and the distance of the free throw line, we can calculate the initial velocity of the ball and the angle that it is released at. The first step of all projectile motion problems is to write down all the variables that you are given. After writing down everything that you are given, choose one of the three equations to work from and a direction that you want to calculate first. We chose the x direction because it is easiest. The reason it is the easiest is because acceleration is 0 in the x direction and because you start at point 0, canceling out many of the steps of the equation. After canceling out the zeros in the equation, you are left with the distance the ball travels in the x direction and the time that it takes to reach the hoop. Dividing the distance traveled by time will give you velocity in the x direction. Since we know the height of the ball, the time it is in the air, and acceleration, we can use these equations to calculate the initial velocity in the y direction. Because velocity is 0 meters per second at the top of the ball's arc, we can cancel out v final. After writing down all our variables, all we have to do is plug them into the equation and solve for v initial. Having the velocity in the x and y directions, we are able to use Pythagorean's theorem to find the initial velocity of the ball. Also, with these velocities, we are able to find the angle using a right triangle. So how does this affect performance? By just increasing the release angle by 3 degrees, you end up airballing the shot. Our next topic is the Magnus force placed on the ball due to the backspin of a shot. This time, as you watch the shooter shoot, watch the spin of the ball. You should see that it spins towards the shooter. Since the ball is spinning in the same direction as the airflow at the top of the ball, the velocity increases and the pressure decreases. The opposite is true for the bottom of the ball, where the spin opposes the airflow and the velocity is slowed, so the pressure increases. According to the Bernoulli's principle, air moves from high pressure to low pressure, causing an upward lift on the ball. With this added lift, as the ball hits the rim, it bounces upward and often rolls in, coining the term shooter's roll.
In basketball, topspin on a ball is most likely observed during a bounce pass, and in this scenario, the top surface of the ball is moving forward with the spin. Under the Magnus effect, topspin produces a downward swerve of the basketball greater than would be produced by gravity alone. For topspin, the difference in speed between ball surface and air is greater on top of the ball since the air flowing past the bottom of the ball is moving faster than the air flowing past the top. As a result, the pressure on the surfaces of the basketball will be lower below than above. There is more air friction occurring on the top surface of the ball compared to the bottom, and this differential causes a greater pressure to be applied on top of the ball. This results in a ball being pushed down. In examining 3 different styles of jumping for our subject, the objective was to understand how to calculate impulse from a ground reaction force, to use impulse to calculate jump height, to determine the relationship between styles of jumping, vertical ground reaction forces, and jump height. To measure jump height, we could record where the subject's outstretched arm touches the backboard and measure the distance from the ground to that point on the backboard in meters. To that distance, we could subtract the height of the subject from his feet to his vertically outstretched arm. Doing so would give us the subject's vertical jump, which is the distance from the ground to the athlete's feet while at the highest point of the jump. The first jump we will analyze is the standing vertical jump. Initially, the subject is in a stationary position, but a quick counter movement before jumping, also known as a pre-stretch, allows the quadriceps to be stretched eccentrically so that the following concentric contraction can be stronger. The amount of tension created by stretching the muscle is depending on the degree and the speed of the muscle's pre-stretch. Utilizing the elasticity of the muscle and the stretch reflex is referred to as using the stretch shortening cycle, which is similar to a rubber band that's been stretched to its extreme and snapped back to its normal tension. Our second jump is the one-step vertical jump. In one fluid motion, the subject takes one step forward and pre-stretches his quadriceps before shortening them. Attaining a pre-stretch of the muscle causes it to be lengthened eccentrically, so tension is developed in the muscle. This stored energy created by tension can be used to help increase the strength of the following concentric contraction. Our third experimental condition involves a subject running before takeoff. Like the previous two conditions, this one involves pre-stretching of the quadriceps, followed by shortening of the muscle. To measure vertical ground reaction force for each of these jumps, we will need to use a force plate. The force plate records ground reaction forces and moments in 3 dimensions and can be used to calculate center of pressure. The ground reaction force is equal to the absolute force applied by the subject to the platform, which is equal to the product of the mass of the person and the acceleration of the person's center of mass plus the weight of the person. From the vertical ground reaction force graphs, we can use the area under the force time curve to determine impulse, which numerically is represented as change in momentum or as the product of the average force and time. We can effectively use impulse to determine max height jumped in meters using the impulse momentum method. We can use the impulse momentum to find the takeoff velocity if we let the initial time be the start of the jump and the final time be the instant of takeoff. If we measure the impulse due to the ground reaction force and subtract the impulse due to the body weight, we'll be able to calculate the jumper's takeoff velocity. Since the time of the jump is the same for all 3 trials, the running trial generates the largest ground reaction force, thus creating the largest initial velocity and the highest jump height.